appears it's clear. Just hope it stays that way. There was a bit of thin haze earlier in the sky, but it seems to be clearing a bit. So fingers crossed that by the time we get it all set up, we'll be ready for you at the end of the talk. So this evening, the talk is building the biggest telescopes, and to give the talk, we've got one of our research students here, Jonathan Crass. Thank you very much.
So I'm going to try and stick to half an hour because I know.
You are going to stick to 1 hour.
I usually get that when everybody. Then you can turn this down a little bit so I don't begin. There we go. So, as Caroline said, I'm a PhD student here at the Institute of Astronomy, and I actually work on building instruments. So, a lot of the time if you come here, you end up with theoretical and observational books, but I'm the one that actually builds the instruments and gets those data. So, what I'm going to be talking about tonight, building the biggest telescopes. Why do we actually want to build the biggest telescopes in the first place? Then I'm going to briefly introduce the telescopes that we have available today. And that's individual telescopes, and if you combine multiple telescopes together. And then finally I'm going to talk a little bit about what we're doing, sort of what's coming online right now, and then what we're going to sort of be doing with telescopes in the next sort of 10 to 20 years. So the all-important question, why size matters? Well, in astronomy, which is what we're talking about, we need to collect as much light as possible, because a lot of our objects that we're looking at are really, really faint. So they can be naturally faint. So we've got things out there, for example, brown dwarfs. They're sort of stars that didn't quite make it into burning like we have with the sun. So they're really, really faint. Or we have objects that are really, really bright, but they're a long, long way away. So if you take, for example, 2 stars that are in the sky, I'm not sure that we can see them tonight, but if you take Betelgeuse and Deneb, which are 2 fairly well-known stars, the people who are out there tonight should hopefully be able to point some of them out if they're available. If you look at Betelgeuse, it's 50 times brighter than Deneb when you look on the sky. But it's actually 10 times closer than Deneb. So if you put them side by side, Deneb would be 4 times brighter than Betelgeuse. So the brightness thing, it could be a really, really bright object, but if it's a really, really long, long way away, you're not going to be able to get much light from it. It's going to look very dim. So what we need to do is collect as much light as possible to do science, which means getting a big, big aperture. So think about this as if we have this light streaming in from space. Think of it like rain coming down. And what you have is you've got a bucket. You've got a big bucket, and you've got a small bucket. If you put a small bucket outside in the rain, you're going to collect a little bit of water, but not that much. If you take a huge bucket outside and put it in the rain, you're going to collect a huge amount of water. That huge amount of water is like the amount of light we collect. So you want to collect as much as possible. So you want the biggest bucket. So you want a really big telescope, which is why the big telescopes sometimes just get called big light buckets, because that's all they're doing is collecting a huge amount of light. So that's one reason we want to do it for looking at really faint things. The other reason is resolution. Now, in optics, there's lots of funky phenomena going on. I deal with these in the lab half the time, and things blow up, and you get to do horrible things with lasers that you don't tell your supervisor about because he'd shout at you. But everything that you do with telescopes is limited in resolution due to what's called diffraction. So, hopefully, maybe not, there should be an equation there, but it's not going to happen. We should have, this is where the blackboard always comes in handy, is what you have is you've got a formula which is resolution, and that equals, for a circular telescope, 1.22 times the wavelength over the diameter of the telescope. It's good to know when technology fails, a good bit of chalk and blackboard comes back to the rescue. So if we've got this 1.22 lambda over the diameter of the telescope, if we increase the diameter of the telescope, this resolution here goes down. It decreases because this number gets bigger. We're dividing by a bigger number on the bottom. This number goes down. And that's good, because this resolution tells us how close we can see 2 objects. They're a long, long way away. If you imagine you've got 2, say, I don't know, these 2 laser pointers, really close together, you can see they're separate. If I went 250 meters away and I said, I got 1 laser pointer or 2, it would get really, really difficult to tell. So the distance apart they are, the closer they are together, if you can still see that distance separation, it's a good thing in astronomy, because you can have lots of things that are close together, stars that are merged together. So you want to make this number as small as possible. One way to do that is get a nice big diameter. The other way to do it is to decrease the wavelength from the top. So that, the other box, which would be wavelength there, would actually be telescope diameter, but obviously it's not there. So that's one sort of way to do it. So you want to get a big diameter and a short wavelength to get good resolution, is the motto of the story. Now, how to do that with big telescopes today? Well, there's different types of telescopes that we use on the ground. So we've got the full spectrum of all the radiation that we know in the universe. You've got the high energy stuff, cosmic rays, gamma rays, and X-rays. So these guys you'll know from going to the hospital. This lot you'll sort of know from getting a nice suntan, and this you'll know from when you want to get nice and warm sitting in front of the fire. If you want to do sort of cooking your food, microwaves are good for that, and then radio is when we do all of our communications. Now, you realise that you're probably not being irradiated by X-rays all the time, because if you stand in front of stuff, you know, you don't put a nice chip behind you, you don't get a nice X-ray emission. And that's because the atmosphere blocks all of that radiation coming in. So as far as we're concerned, on the ground, we don't care about that. The other bit we don't care about is the really low radio waves, because that reflects all of that low energy radio radiation back out. So we're left with all of this stuff that we can see on the ground. Now it's not quite as simple as that, because then there's bits of some bits you can see and other not, and other bits you can't. So this grey stuff, we can see parts of this, but we can't really do it very well from the ground. So as astronomers, we like to be as efficient as possible. So we generally don't look at any of this stuff on the ground very much. What we look at is the visible, and usually the radio. So that's what I'm going to focus on. So radio telescopes. Well, these have been around since about the 1930s, when a guy who was called Karl Jansky, who was at Bell Labs out in the USA, was basically, they were having trouble with their telephone network that was done over radio. And his boss said, figure out why it's not working properly. So he built this radio detector to try and figure out what this stuff was. And he just sort of said, well, there's something coming from space, but I'm not really sure what it is. So people went and developed this further. This was the first sort of telescope that was built by Jansky. It doesn't look very much like the radio telescopes now, because it wasn't very sort of directional. But what he could say was, I've detected something. I'm not quite sure where it's coming from, but I've detected something. Which was something interesting in itself, but not very, very useful. So then we started doing a bit more. And there was another guy called Grote Reaver, and he built the first sort of dish telescope that we ever see. So this looks a bit more like a normal telescope that you're used to seeing. It's not fully steerable, it only moves up and down, but it's still a telescope. And he sort of detected other bits and pieces from the sun, from the galaxy. Now, after that, other things started happening. So, rapidly developed work in Australia and Britain and the USA, and that was because we hit World War II, and we developed radar, which was the emission of this radio stuff and then seeing what's bounced back. So this rapidly developed how all the detector systems and everything, which meant by the time the war finished, we had a much better understanding of all the technology involved. And it meant by the time we got to 1957, there was a 76 meter. So this room's probably about, I don't know, 10 meters, 15 meters across, side to side, maybe 20 pushing it. About 4 times the size of this room, 1950s, 1960s, a radio telescope. And that was the Mark I radio telescope up at George Bank near Manchester. So this was built between 1951 and 1957. And it was rushed at the very end because we were in the middle of the Cold War, and the Russians had just launched Sputnik. And this was the only thing that could actually track this thing in the world. It was the only radio telescope that could be steered in any direction. Even today, it's still the 3rd largest steerable radio telescope in the world. So it's still a really, really important science instrument. And it's a lot older than I am, so it's not doing badly. The total mass of this thing is about 3,200 tons. And the quite amazing thing is it's 76 meters across, and the surface of it is accurate to about a millimeter. So if you imagine kind of trying to build something 4 times the size of you and getting accurate to a millimeter in the height of the surface, it was pretty amazing that they managed to do it really well at the time. And it's gone through multiple variations, and this is what it looks like today, hopefully. So it's gone through multiple different surfaces, and its detectors and things have improved. But the basics of what they did back then are still what we do now. It's a pretty neat piece of kit. And I've actually been up inside of it, and it's really cool, because you can kick a football and it comes clap, so you never get second place. So, biggest radio telescopes, that's sort of the oldest big one. The largest field aperture one, hopefully, there we go, is the Arecibo radio telescope, and that's 305 meters. Now this one isn't fully steerable, it's basically built into a massive sinkhole out in Puerto Rico, and this detector in the middle moves around as they can adjust basically the location of it, and look at sort of things about 20 degrees from the vertical, but it's not fully steerable like the one, the George Bank telescope. So that's 305 meters. The largest fully steerable one is the Greenback telescope, and that's out in America. Now, there's the Emmitsburg telescope out in Germany, and that's 100 by 100 meters. Now, the Americans wanted to have the biggest steerable one, so instead of making it circular, they decided to make it elliptical, so it's 100 by 110. Purely, the reasoning seems to be purely so they can say they have the biggest telescope. And then finally, the biggest actual radio telescope overall is one that's out in Russia, and that's half a kilometer, over half a kilometer. Now this thing looks a bit weird because you kind of go, well, there's nothing in the middle of it. So this isn't actually very sensitive, but it's got very good resolution. So if you look around the edge, there's lots of these panels. What it does is it reflects all the radiation into a detector in the center and measures it there. Because there is no way that you can really try and do a 576-meter telescope and fill the whole thing in unless you have an awful lot of money, which is what science usually boils down to. So that's radio telescopes. The other thing I said was we can look at the optical. And that's what we're used to seeing, all these optical telescopes. And it's a bit more sort of conventional. So the first optical telescope is a little controversial. Apparently it was done by Galileo in 1609. But he actually sort of stole someone else's idea, but he just made it better and made it work. So you can argue that one all day, but it's usually attributed to Galileo. And this is him with a picture of his telescope, and this is an actual photograph of what the telescope looks like. It's got two lenses in it that magnify the image. I think this one has a magnification power of about 20, so nothing massive, but considering all they had before this was basically the naked eye, seeing things 20 times bigger is actually a pretty big step up. So that was Galileo. Since then, we've gone a little bit further. So, as I said in that telescope, you use two lenses. And that, when you use that kind of technology, it's called a refracting telescope. Now, the Northumberland telescope, for those that you've been here, is the one that's outside, and hopefully you'll be using it, has an 11.6-inch glass lens at the top, and then has another eyepiece down at the bottom, which gives you the magnification for when you're looking through it. You can actually change this one here, the eyepiece, to get different magnifications depending on what you're looking at. But the principle is exactly the same as the first telescope that was built by Galileo. The problem with that is you've got a nice big piece of glass. And nice big pieces of glass are, one, fragile, and two, not particularly easy to get rid of all of the optical effects in them, because they have, if you've ever put light through a glass prism, it separates out into different colours. So you suffer what's called chromatic aberration, so if you can call it technically, it basically means the different colours of light spread out, which if you're trying to look at something isn't particularly helpful. So that's the original thing. Since then, we started using mirrors. And that did become popular sort of the end of the 18th, 19th centuries, when you could actually start building mirrors quite accurately, coating them nicely, and it started replacing them. So this is the 60-inch Hale telescope out in California, and that was completed in about 1908. It was sort of the first big-sized mirror telescope that could be used. Since then, things have got a bit more complicated, but that's because it's a lot easier to make mirrors now. So pretty much every single telescope you will see today is a reflecting telescope using mirrors. So that was 60 inches. We decided that that wasn't big enough. So we kept going bigger and bigger and bigger. So by 1918, we had a 2.5-meter telescope. 1948, we were at 5 meters. Went down a little bit in the interim, and that's usually because of science reasons of what you're trying to look at. But then, 1993, we get to 10 meters. And that's pretty much been the baseline. We've had other sort of similar sizes until in the last few years we've had a new telescope in La Palma in the Canary Islands, the Grand Telescope Canary Islands, which is 10.4 meters. Again, you notice the difference between 10 and 10.4 isn't that big, because they wanted the biggest telescope. So, I think a lot of the time in astronomy we learn to go, ours is bigger than yours. Anyway, what I'm going to talk about is a very large telescope, and there's a reason that they built 4 of these together, and that links into what I'm going to talk about in a bit about combining multiple telescopes. So, building the VLT, the Very Large Telescope, the really original in astronomy of our name. So it's built, it was part of the European Southern Observatory, which today is a collaboration between 15 different countries. 14 officially, but Brazil's joined in, it's just their government hasn't officially signed the paperwork yet. Now, back in 1987, there were 6 members of this. The UK wasn't actually until 2002, but they decided that they were going to build 4 8-meter telescopes. And these are the guys that are very, very happy, sat around this table. I'm glad I wasn't there because it was a very long meeting, but hey. So in December 1987, they decided they were going to actually build this set of telescopes. So then there's lots of questions when you want to build a telescope. First one, where are you going to put it? So they had a site down in Chile already, but they were like, well, it's good, but maybe there's somewhere better. So they started looking. And by 1990, they decided that they were going to choose a different site, and that's called Paranal. And basically, the reason was it has more clear nights. And if you're trying to look at stars, if you're in Cambridge, it's cloudy a lot of the time. It disappoints people when they come here on a Wednesday. But if you're going to build several £1 million worth of telescope, you want to be able to use it as much as possible. So you want it nice and clear. So that's why they chose their site in Paranal. The next thing you do, you've chosen a site, let's build the thing. Fine? Sounds nice and easy. Problem 3, deal with the politics. So the Chilean government decided that they didn't like what ESO was doing and went back on a few plans. And it delayed things slightly, but they eventually sorted that out. Once you've done all of that, you kind of go, well, how much did it all cost? So, you know, we're not talking a nice little telescope here, we're talking 4 8-meter telescopes. So I can give you a number of 602 million Deutschmarks. Now, some of you might even remember the Deutschmark. I remember the name, I have no idea how much that is. So if you convert that into today's money, it's about 307 million euros. Quite how much that will be tomorrow with the euros going, I'm not sure, but that's the way. It's about 300 million, so it's about sort of a third of £1 billion, give or take. So you find your site, Paranal, then you build the thing. So the first thing you do is level the site. And when I say level the site, I mean you take the top of the mountain off. So this took about 2 to 3 years of basically blowing the top of the mountain off and taking it down again. So it was a nice top of the mountain up here, and it ends up like this. So 3 years, you had a nice site to actually build the thing on. And then give it another 5 years, you have pretty much the site set up. So just to show it in, these are basically the 4 pits where the main telescopes are going to go, so you can build the foundations. There's a control room that appears here, and then all the rest marks out some of the other science instruments that are made. So if you do that, you've got this nice building here, you've got 4 telescopes, this one has been finished off, and then all of this other stuff is marked out. So it's pretty neat that they actually, you know, what they did the first time was actually done. You've built the telescope, you've built the site, but you've built the enclosure for it, you haven't actually built the telescope. So what they did at the same time in 1991, they went and built these 8-meter telescopes, 4 of the things. So they cast them out in Germany, shipped them to France, then shipped them across the Atlantic, they got to Chile, and then you have to actually get them up the mountain. Because this is on top of a mountain, it's about like 15,000 feet up. Long way up, long way from the coast. So you transport this thing on roads. There's 2 lorries here, because this thing is so heavy that they basically have to combine these 2 and drag it up the mountain. You get it there, and they say, excellent, it's you. They give a nice big welcome to the first mirror that gets there. So that was 1 out of the 4 for all the telescopes. And then, watch it up. There we go. So this thing rumbles along in a nice big convoy, and you can see that the enclosures are up at the top here, and it's trundling along. And I think I counted about 6 sets of wheels on 4 different sets of them, so you can just see how heavy this thing is. You can also see how accurate this thing has to be in a minute. So what they do when they get these things to Chile is they don't bother coating them in France, they coat them when they get to Chile. So there's a nice big glass plate, and then they put a nice shiny surface on, like you'd have in your mirror at home, you put some kind of metal on it. What they do on here is they put aluminium on. and it ends up being 80 nanometers thick. So this is an 8-meter telescope. Think about the size of the floor down here. And they put 12 grams of aluminium on the surface of it. That's less than a Coke can spread across the entire surface of this thing. So it's really, really thin, but that's all they need. And they recoat these every 18 months to keep them nice and shiny for good size. So that's that. Put it all together, and you should get a nice shiny image. So this, if I'm just going to turn the lights down on this one, hopefully. There we go. So this thing is Centaurus A, which is an active elliptical galaxy. And it actually shows you in here, the dark regions are dust. So down here is all the dust. And then the lighter regions are where we've got sort of emission and light coming through from stars and other things in the galaxy. So this was the one of the first ever images they took. We've had better ones since then, but the principle of they could actually build a thing and it sort of worked first time was actually kind of neat. So that was what they did. The next thing is, well, let's go back to talking about combining telescopes. You've made your first big telescope. Fine. All of those little trenches and things you saw on the VLT were because they want to connect those telescopes together. And there's a good reason for doing this. So, very large telescope, and if you go back to the radio telescope, we want to think about resolution here. We're not talking about light collecting area, we want to talk about resolution. So a very large telescope, it's 8.2 meters, it looks at about a wavelength of 650 nanometers. That's the visible light, that's what we look at. It's about what this laser pointer is, about 650, give or take. The Lovell telescope, that big radio telescope, 76 meters, and it looks about 21 centimeters. That's a nice radio light. Resolution is the important thing. So that's about 1/200,000th of a degree. It's pretty small, but it's still not great when you're talking about astronomy because things are really, really long, long way away, which means they seem really close together. Radio is rubbish. It's a 1/5 of a degree when you're talking that thing, purely because the difference in wavelength. So as I say, if you have a shorter wavelength, this is much, much shorter than this, you end up with a much poorer resolution if you go for a longer wavelength beam. So that's the reason for that. Now, it's not as simple as that. In the optical, stars twinkle. If you go outside and look at that, you see it any night. And that means that the resolution of the telescope goes down because of the atmospheric effect. So we use adaptive optics to try and correct for this thing. But it's not perfect yet. When it is, it'll be fantastic. But until then, we still can't reach the actual perfect resolution to get a fantastic telescope. So the way we get around this and get better resolution is using what's called interferometry. So it's usually been done with radio telescopes, and it was actually pioneered down here in Cambridge across the road at the Cavendish Lab, and there was a Nobel Prize for it back in the 1970s, if I remember correctly. And what you do is you take radio telescopes and you connect the signals coming into them together. And you see what happens when you merge them together, what you get spat out, basically. There's a lot of funky computing goes on in that, and it needs lots of big computing power. We'll come back to that in a minute. But it works. And it acts as if the telescopes, the two telescopes, you don't care what size they are. It basically means if you've got a telescope in Cambridge, and you happen to have another one up in Manchester at Georgia Bank, if you connect the two together, you get an equivalent telescope as if you had a full telescope between Manchester and Cambridge. Now, we've got Birmingham in the way, so some people might not care about Birmingham, so you could build a telescope over it. Some people quite like it. But I mean, building that kind of thing is just physically impossible engineering-wise, and you haven't got the space. So using this interferometry technique, you get much better resolution because you get an effective telescope that's several 100,000 kilometers in diameter, rather than 76 meters, which sounds tiny in comparison when you compare to 8 meters, it sounds huge. So the principle of how it works, well, you've got two incoming signals, one from one telescope, one from another telescope. You combine them together. If they match up nicely, you get a nice big signal. So you can see the peak of this one matches up with the peak, the trough matches up with the trough, the peak matches up with the peak. A nice big signal, they all line up. If instead of the second one, you've got a peak and you've got a trough coming in on the second one, they don't match up, you get no signal at all. And by looking at what you get between the telescopes and moving them around, you can basically figure out what's going on. You get a nice big signal. And this works. So in the UK, we've got what's called the Merlin array, and this is several telescopes, 7 in this image, spread all over the south of England. So we've got one down in Cambridge, there's several up in Manchester at Georgia Bank, and then others spread around. In total, they're all linked together. They used to be linked via microwaves, but they've recently upgraded this to what's called email. So that now uses fiber networks. Now, I did my undergraduate at Manchester, and they tested this for the first time. And they routed it through the university's internet connection, and basically swamped it. They switched it on, the university's internet ground to a halt. They had a guy from the computing service phone who would turn it off now, which was certainly interesting to be there, where they did that. So they get all of these signals coming through the fibers, they combine them together. This is the computing black box that I really don't want to talk about because it's horribly complex, but it's just like we have it those ways, adding up and basically cancelling out, and you get some kind of image. For this one, we have an effective diameter of 217 kilometers. We're not talking meters now, we're talking kilometers, it's huge. Giving 1/90,000th of the resolution. So, pretty good, really, considering we're at a fifth of a degree before. Now, we can take this to the extreme. That was England, that's up here. We can now do this across the entirety of the length of the Earth. So that's when we start talking about very long baseline interferometers. Again, very long baseline interferometer. We're not really very good with our names. These are all now collected with fiber. They used to be done with tape, but it means you fill up a DVD equivalent with data in about 32 seconds. Lots of data flowing around. It's all done with fiber links now. And this means you've now got an effective telescope diameter of about 12,000 kilometers, giving you a resolution of 1/46 millionth of a degree. So you've got fantastic resolution of these things. Not very sensitive, because you've only got a tiny small part of that telescope covered by these individual telescopes. But for resolution, they're fantastic. And just as another picture, you've got loads of telescopes that connect all around the world together, making these fantastic images. So, that's what we have now. What about the future? Well, ALMA, or the Atacama Large Millimeter Array, works in the millimeter and sub-millimeter bands, and is looking at sort of star forming and different things like that. Now, the neat thing about these telescopes is it's not like what we talked about with Merlin and the other one, where you've got a fixed set of telescopes. These things get picked up and carried around, so you can put them where you want, depending on what science you're going to do. So this is up at about 18,000 feet out in Chile again. There's 66 telescopes, about 12 meters in diameter, and these all get combined together into computing power. Into a correlator that gets you the signal, gets you the science. When I said you need computing power, Merlin had about 7 telescopes at once, and it has a huge room in Jodrell Bank that's a lead-lined box because it emits a load of radio emission, and it's next to a radio telescope, so it's a big solid lead-lined box. This correlator is the highest, most powerful computer that's been built. But what we're about to come on to next, this is nothing in comparison. So the resolution of this thing is about 1/3600th of a degree. It's pretty neat. And, you know, price now, we're not talking millions. This costs 1.3 billion euros to build. This has just started coming online. The thing I really think is it's just like boys and toys, really, when you pick up a telescope and put it on the back of a truck and cart it around. So this is one they were moving around when they were setting them up in the last few months. So that's ALMA. The next thing that I want to talk about is the square kilometre array. So ALMA was 66 telescopes over about 16 kilometres. The square kilometre array is a radio telescope that's going to be spread over about 3,000 kilometres, either in South Africa or Australia. If you've been reading the news, apparently it's being leaked, it's one of the two, but they're denying that, so watch this space. It's got thousands of detectors and dishes that are spread in different configurations. And the effective thing about these is they're going to have a total collecting area of 1 square kilometre, hence the square kilometre array. So in most of these big telescopes, they only have very few elements. So they have brilliant resolution, but not very good sensitivity because they don't collect much light. They don't have a big bucket. With this thing, you're going to have a bucket that's equivalently, you know, a kilometre by a kilometre, effectively, which is a really big bucket. And if it was raining on it, you'd collect an awful lot of water, so you'll collect an awful lot of light. This shows the central region, but as I say, it's a radio telescope. It's 1.5 billion euros this time, so a bit more than ALMA. It's 1 square kilometre in area, and it's spread over 3,000 kilometres from the centre. So 6,000 kilometres overall. South Africa, Australia, and then finally it should start science in 2019. Hopefully it'll start building in 2016, and it should be finished in 2024. So pretty neat. That's the biggest thing that we can do combining telescopes together, and it's ridiculous. They have no idea how they're going to do the computing for this at all. It's just completely incomprehensible now. They're just kind of hoping that Intel or NVIDIA will do some magic and we'll get some fantastic computing power to be able to handle it. But they've got a few years yet, so we're not panicking too much. Anyway, moving on. Then we get back to individual telescopes, and that's where the optical work is being focused on. So there's currently 3 proposed super-sized optical telescopes. There's the European PLT, which is supposedly 42 meters. It's been scaled down a little bit, probably about 39.3 now, and it'll probably get cut a little bit more because of budget costs. Then there's the 30-meter telescope, and there's no guessing how big that's going to be. And then there's a Giant Magellan telescope, which is 24.7. So this one's going to be a European one down in Chile. The 30-meter telescope is planned to be up on Hawaii, and this Giant Magellan telescope is planned to be out in Chile as well. Now, cost-wise, we're talking €1 billion, $1 billion, and then, cheap really, this one's only 700 million. Cheaper than close. So, it's a bit ridiculous. Now, what I'm going to leave you with is a little movie. This is the prep talk for the European ELT. Hopefully. This is their sort of marketing video to try and sell it to you in your tax bill. So the important point to remember is that size really does matter, at least when it comes to astronomy. And we can build bigger telescopes. We already do it. We can build them on their own. We can combine them together, which means we don't get as much sensitivity, but we get really good resolution. And future telescopes are going to use a combination of both methods depending on sort of the wavelengths you're looking at. So that's it. Thank you very much. And if there are any questions, thank you.
Very difficult as optical wavelengths to do this interferometry compared to the radio.
So the question there was, can you basically do this interferometry combining the two telescopes in the optical? And the answer is yes. And that's what they're doing at the VLT. This is why they built the 4 8-meter telescopes. And they also have a load of smaller telescopes that they moved around all of the stuff that was there. But it becomes much, much harder, purely because you have to have everything so much more accurate. So in the radio, you've sort of, one wavelength is about 50 centimeters to a meter, roughly. At the optical, you're talking a fraction of a meter, which means everything else has to be aligned so perfectly that it's really, really technologically challenging. If you're saying, I need to have this accurate to a couple of nanometers, well, on the telescopes, the mirror coatings are only 80 nanometers. So, you're looking at something that has to be really, really accurate, and that causes a lot of problems. They've done it, and then working on it, but it's still sort of a work in progress until it becomes really, really powerful. Any other questions? Yep.
If you have this really good telescope, then can't you adapt it? Obviously, if you have the money, and then send it up into space, then it's even closer to it.
You could. So what we'd love to do with telescopes is to put every single one in space, because it would get around all of this atmospheric effect stuff. If you have a fair sort of, you can make the rocket technology to do it, and then you have a few billion pounds, then sure. But the problem is, as soon as you go into space, it gets several tens of times more expensive to do it. So it's all to do with money. It's cheaper to figure out how to fix it on the ground than it is to actually send it up into space. Which is why the other reason that what I work on is trying to correct those atmospheric effects. Because when the Hubble Space Telescope stops working, which eventually it will, and we're not going to go and repair it anymore because we don't have the shuttle fleet, we won't be able to do really, really good high-resolution imaging in the optical. So people are really looking at trying to fix that now. But we'd love to go into space, it's just money, as always. I'll take one more question and then I'll let you go out because I can see you all wanting to go. Yes?
Would it be possible to use the Earth's orbit as a really large baseline?
Yes. So that was, if you want to, you could use, say, the Earth's orbit for this interferometry, and the Japanese have actually done it. They've actually sent up a radio telescope and have combined it in with the ones on the ground. Again, the problem with that is the sensitivity, and if you only have 2 dishes, it becomes, you don't get a lot of information back. You need several telescopes. So, as I said, it's expensive to send one telescope into space. Sending a whole collection of them gets really, really prohibitive. So, it's not that it's impossible to do. It's a case of, I think, people are now trying to focus on getting more light and building lots of detectors, hence the square kilometre array, where they're going lots of telescopes, lots of sensitivity, rather than resolution. So it's that trade-off. But in theory, yes, you could send it into space.
I was thinking more of taking measurements 6 months apart.
Yes.
From Earth.
No.
From Earth.
No. So the thing with interferometry, usually you need to combine them together. Well, no, in theory you could, but I don't think it's ever been done. But in theory you could map it. It would still only give you a very small amount of information though, because compared to the distances, all the telescopes are very much close together. You want to get a spread across the equivalent distances, which is why when we had that map further back, you had all the telescopes spotted all over. Because you want a nice spread across it to get a lot of information, whereas you'd have the Earth here and the Earth here. But it's, 15 million kilometres either side of the sun. It's 30 million kilometres, but you have these telescopes clustered within sort of 10,000 kilometres either side. So you have a lot of clustering either side, but not a lot in the middle, so you wouldn't get a lot of information back. But in principle, yes, you could. Right. If anyone else has a question, I'll be at the front. Otherwise, I'm hoping Carolyn should be able to play away.